So in this lesson, what we're going to talk about is we're going to talk about the basic idea of continuity. So let's first start out with a definition, because definitions are really important inside of calculus and in math just in general. So definition, a function f of x is continuous at a number a if the limit as x approaches a of f of x equals f of a. Alright, so a couple things that I want to point out inside of this definition. One is that it's continuous at a number a. So what we're talking about here is at only a single value for x, right? It's this a right down here inside of that notation, okay? And then what we're going to say is that we're going to define that. We're going to say we know that the function is continuous at a if the limit as x approaches a of f of x equals f of a. Done. Okay? So let's take a look at an example and let's talk about what this kind of looks like so we can kind of picture it inside of our minds. So let's imagine that I've got this function and it's f. There's f. Okay? And here is a. It's on the x-axis. And then, well, if we look here, we go up here to the function. And so on the y-axis, here is f of a. Okay? Now what I'm going to see here, if I kind of look at this and I think about what I understand about limits, I'm going to think, okay, so as I approach a, right, from the x side, what do I approach on f of x? I approach f of a, right? So coming in from the left side, I approach f of a. Coming in from the right side, I'm also approaching f of a, okay? So it looks like the limit as x approaches a of f of x equals f of a. Great. All right? So that's what it looks like, okay? In fact, right, if we know, let's say, for example, if f was a polynomial, we know we could substitute. And get f of a for the limit as x approaches a of f of x. Alright? So that's just an example. Hey, you know what? What happens here is that I actually just hit that point, all good. Okay? Right? So, f is continuous at a. It's continuous at the point. Let's look at an example where it's not continuous, okay? All right, so if you remember, we had this thing, we had the heavy side function, okay? There that is, right? Now, if I wanted to say, so let's say, for example, this is a equals 1, okay? And what we get here is we want to know the limit. Is f continuous at x equals 1? So if I look here, I'm going to say, okay, the limit as x approaches 1 of f of x, right? Well, let's see. So here's a equals 1, okay? Coming in from the left-hand side, right, it does appear that it's going to equal 1, right? So the limit as x approaches 1 from the negative side is equal to 1. On the other hand, if I came in from the other direction, okay, if I came in from the right-hand side, right, the limit as x approaches 1 from the positive side of f of x equals 2. It's a problem, okay? Actually, this isn't the heavy side function. This is the greatest integer function. But nonetheless, same idea. What we see here is we see that these two, okay, they're not equal. So the limit as x approaches 1 from the positive side of f of x does not equal the limit as x approaches 1 from the negative side. So the limit as x approaches 1 of f of x does not exist. Right? So f is not continuous at 1. All right? On the other hand, if I looked at it and I said, okay, well, what about a equals 0.5? Is it continuous there? Well, if I look here, right, okay, coming in from the left-hand side, okay, I get the limit as x approaches 0.5 is going to equal, right, 1. And from the positive side, or from the negative side. And then coming in from the other side, from the right-hand side, what I get is I also get 1, okay, for my limit on both sides. And so consequently, they agree. Ooh, so the limit equals 1. That's great. So like if I look here at my opposite side, the limit as x approaches 5 of f of x equal, or 0.5, excuse me, is equal to 1. Well, good news too, that f of 0.5 also equals 1. So, if you look at your definition, since the limit of as x approaches 0.5 of f of x equals f of 0.5, which equals 1, f is continuous at 0.5. So it in fact is continuous at that particular point. Oh, awesome. That's great. Okay, so I got continuity there, so I got continuity at 0.5, but you see, at a different point, at 1, I got a discontinuity. So that's what I'm talking about when I talk about something being continuous at a point. Okay, we define which point that we want to look for continuity on, and then what we do is we make a determination about whether or not the function is in fact continuous at that point. There it is. Okay, that's the deal. So now that we've talked a little bit about what it means to be continuous, okay, and it's really that simple, right? You show that the limit, okay, as x approaches, you know, this particular point equals this value, and then show that the function actually equals that value. Okay, so let's talk about and categorize some discontinuities. Okay, so a discontinuity is a point on the function where the function is discontinuous, where the function is not continuous. Okay, so let's start out with what we call a jump discontinuity. These are kind of the easiest ones to see. All right? This is a jump discontinuity. This is a jump discontinuity. The limit does not exist at this point. At this point, because the limit as x approaches a from the positive side of f of x does not equal the limit as x approaches a from the negative side of f of x. There it is. Okay? Or, okay, do we just have that the limit as x approaches a, right, does not exist? We can't even say that it equals infinity. It's like, for example, if we had a big gap, right? If there was a gap inside of the graph, okay, and we had, you know, a was right in the middle of that gap, yes, and when I talk about a gap, I mean a gap on the x-axis. We'd say, okay, that's a jump discontinuity too. Here, what we can see, right, is that as we approach a from the negative side, we get whatever value this is, call this f of a1, or not f of a1, excuse me, but call this y1. And then down here, as a approaches it for the positive side, what we get is we get y2, right? So two different y's for f of for the limits, and so consequently those limits don't agree, and so they don't exist. All right. So that's a jump discontinuity. Is when we have an asymptote. Okay. It's basically when we have an asymptote. All right. So I imagine something that looks like, for example, like this. Okay. As it extends up towards positive infinity. So if we look at this, we might say the limit, okay, as x approaches a of f of x equals infinity. Okay, so f is not continuous. Actually, x equals a is actually x approaches 0, if you can see in this graph. So f is not continuous at 0. Right? There it is. We're just saying not continuous at that particular point. That's an infinite discontinuity. It doesn't have to be both going up towards positive infinity. One could be going towards positive infinity, the other one going to negative infinity, right? But the asymptote represents a discontinuity. It's breaking up the graph, right? That's what's happening. It's breaking up this function, right, into separate pieces that we can't actually deal with, okay? So consequently, this is what we call an infinite discontinuity. This is a discontinuity that you can actually eliminate by changing the function, okay? We can eliminate the discontinuity by creating a piecewise function. Okay, so let's take a look at one. Let's say, for example, I have the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, now at f of x, or at f of 1, we get this equals, it does not exist, right? Okay, because, right, x squared, or actually, excuse me, because 1 squared minus 1 over 1 minus 1 is 0 over 0, and we can't divide by 0. Right? So it does not exist. So we got a problem there, right? Clearly, the limit as x approaches 1 of f of x does not equal f of 1, because f of 1 doesn't exist. F of 1 does not exist. Okay, D and E does not exist. All right, however, here's the thing. A little algebra will allow us to change this. So I'm going to take x squared minus 1 over x minus 1, and that's going to then equal x minus 1 times x plus 1 all over x minus 1, which just equals x plus 1. Right? That's how we would actually go about finding the limit. In fact, we'd say, okay, well, so since this is true, right, then we know that the limit as x approaches 1 of x squared minus 1 over x minus 1 is going to equal the limit as x approaches 1 of x plus 1, which equals 2. So that, in fact, is going to end up being our limit there. So we know that f of 1 doesn't exist, but we do have a limit, all right? And so what that's going to do is that's going to kind of help us out with figuring out how to remove our discontinuity, right? We're not removing a piece of the graph. We're actually going to remove the discontinuity. We're going to add something to the graph to make it continuous, okay? So let's take a look at a graph, and then let's talk about how it is that we're actually going to, in fact, make this continuous. Remember, make sure that you have this written down because it's going to end up being really important. let's draw a graph. Now, if you go into Desmos and you actually put in x squared minus 1, right? So we have f of x equals x squared minus 1 over x minus 1. What you're going to get is you're going to get this thing that looks like this, okay? It's going to start at 1, right? And it's in fact going to be like a perfectly straight line, and it won't have a little hole in it. But if you run your marker, right, if you run the cursor over the line, what you'll get is that this ends up being, it's undefined, right? Undefined at x equals 1. All right? So that's our problem point. However, the thing is that, you know, f of x equals x squared minus 1 over x minus 1 is just equal to x plus 1, right? Except for at that one little point, right? At that point in which it's undefined. And that's why we end up with this graph. That graph is a graph of x plus 1, except for the fact that it's missing that point, okay? It's missing f of 1, okay? But if I look here, right, okay, at 1, so if I look here at 1, all right, what I see is that the point that I'm missing, okay, is at y equals 2. All right, so we should have 1, 2, right? That's our missing point. So like the idea here is that I'm going to say, okay, well, I'm going to pop it in there, right? Okay, I'm going to say, okay, I'm going to redefine my function, all right? I'm going to say, okay, so in order to make my function whole, to remove the discontinuity, okay, from the function, I'm going to create a new function. I'm going to call it g of x, okay? And so g of x is going to equal x squared minus 1 over x minus 1 if x does not equal 1. And it'll equal 2 if x equals 1. And there it is, okay? What we've done here now is we've filled in the hole. Filled in the hole, right? Now I actually have a continuous function. In fact, watch this. The limit, okay, as x approaches as x approaches 1 of g of x is going to equal, well, it's going to equal 2, right? You can see that. Will equal 2. In fact, the limit as x approaches 1 of f of x, and you can try this out yourself, we saw it before, is equal to 2, right? Okay? And for g of x, g of 1 equals 2, because that's what the piecewise function says. Okay? So, we'll take this little piece here, move it over here so we can do a little writing. Okay? So, g of x is now continuous at x equals 1. We've removed the discontinuity. And that's what it means to be a removable discontinuity. Here's the thing about removable discontinuities. Generally what they are is they're ones like this, okay? Right? We can remove the problematic area, right, using algebra. Okay, so let me write the problem part of the function using algebra. Basically, if it cancels. And that's what makes something a removable discontinuity. There it is. So we've got 3 kinds of discontinuities. 3 kinds of discontinuities. One, we've got the jump discontinuity. That's one I can't take care of. Right? Basically, there's a hole in the graph at the point A. All right? Not a hole, excuse me. There's like a gap. Right? Some kind of gap. The limits going from the left and the right don't equal each other. So consequently, I can't compromise that. There's no way to deal with it. 2, another one that I still can't deal with, is the infinite discontinuity. That is that there's an asymptote. There's an asymptote at A. And the third one is the removable discontinuity, which which I can actually repair by creating a piecewise function. So we call that, that's a repairable one. That's what I'm going to call it. That's not necessarily what they call it. It's just removable. Okay? So those are our three kinds of discontinuities. Oftentimes when you're thinking about continuity, it sometimes is really helpful to think about it in terms of what is discontinuous, right? Okay? A continuous graph is one that's, there's none of those problems. There's no problem areas. There's no place in which the function's undefined. There's no issues anywhere, okay? And so consequently, what you have is you have something that's continuous on an entire interval, right? Okay? That is the interval, right, is an entire set of values along the x-axis. And we look at it and we go, okay, in that interval, I'm going to have no jump discontinuities, there are no infinite discontinuities, and there are no removable discontinuities. Okay? Really important. It's an important kind of like, you know, idea. We're going to look at that in just a second. So now let's define something being continuous on an interval. So now, instead of just looking at a single point, we want to know whether or not something's actually continuous on an interval. Really, be careful about words and language, because this is a totally different idea. This is actually saying, okay, let's say, for example, I have an entire range of values. Okay, I have a range of values, and I want to know whether or not they are continuous on that interval. All right, on that range of values for x. Now, in some cases, right, this can be actually really hard to do. All right, and we do this in much more advanced math classes. But sometimes it's actually pretty easy utilizing some theorems. So first, let's talk about, you know, kind of the idea of being continuous on an interval, and then let's look at some theorems that'll just help us prove something is continuous on an interval. Okay? So let's we got our definition. A function is continuous on an interval if it is continuous at every point in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. And I'll show you what I mean by that in just a second. So let's take a look at, say, for example, a graph like this. Okay? Clearly there's an asymptote, right? So we have an asymptote at x equals 0. So that's a problematic point. Asymptote at x equals 0. So this is not actually going to be continuous everywhere, and we'll talk about continuous everywhere in a minute. But if I look here, it does look like, right, okay, from negative infinity to 0, okay, the function is continuous on that interval. So that's what they were talking about when they talk about, say, for example, in this case, the rightmost endpoint. The rightmost endpoint of 0, not including 0, so does not include 0, is included in the set, okay? So this doesn't include 0, but we're actually just talking about the limit as we approach 0, right? And do we get something as the limit as we approach 0? Yeah, it's going up to infinity. It's extending out and extending on infinitely on the graph, okay? But also, from 0 to infinity, the function is continuous. And we can see that as well. Right? Our limit, right, basically as we approach 0 from the positive side, okay, so as we approach 0 from the positive side, is going to end up equaling, right, negative infinity. But that's okay. That's not a problem. As long as we just, you know, we're keeping going, right? It keeps going. There's no breaks, right? So what we have here is we have it's continuous on this function f is continuous on the intervals negative infinity to 0, and it's also continuous from 0 to infinity. Okay? So it's continuous from negative infinity to 0 and 0 to infinity. That's great, okay? But this function is not continuous on negative infinity to infinity, not on the entire real number line, because the limit as x approaches 0 does not exist. Or the limit as x approaches 0, yeah, does not exist. Because limit as x approaches 0 of f does not exist. So what we can see is that we've defined what the intervals are where it is continuous, and we've said, okay, but it's not continuous at this particular point, right? And that's what we talk about when we talk about continuity on an interval. From negative infinity to 0, this function is continuous. From 0 to infinity, this function is also continuous. So it's continuous on those intervals, but it is not continuous everywhere. All right, so let's ask ourselves, how would we go about determining if a function is continuous on an interval? And so what we have here is we have basically some theorems that are going to allow us and help us to really think about determining if a function is continuous on an interval. And then I'm going to demonstrate a little bit about how we go about using these in order to prove that a function is continuous on an interval. So, if f and g are continuous at a, and c is a constant, then the following functions are also continuous at a, right? So basically, if we know that f and g are continuous, then we know that the addition of them is continuous. We know that the subtraction is continuous. We know that if we multiply this thing, c is called a scalar. C is called a scalar. It's basically just a number that you're multiplying by. Okay? A scalar times the function, also continuous. F times g, so multiplying the two functions together, that's going to make it continuous. And f of g, f divided by g, if g of a does not equal 0. Okay, so if we know that the function actually doesn't equal 0 at a certain point. Great, so that's really actually going to end up being really important. So just remember that the addition, or maybe not remember, but study, the addition of two continuous functions is continuous. The subtraction of two continuous functions is continuous. Multiplying a continuous function by a scalar, continuous. Multiplying two continuous functions together, continuous. And then if we divide, we're also going to get something that's continuous. As long as we don't get 0 in the denominator, right? Because that's always going to be a problem. Great, cool. Well, awesome. How do I know that f and g are continuous then? Because that would be great. Then I could just say, there's just an addition of them. Well, we've got two more theorems that are going to help us out with this. One is to say that any polynomial is continuous everywhere. Awesome. So that's good to know. So if I have a polynomial, and so, if you need to look up what a polynomial is, go ahead and do it, right? But any polynomial is continuous everywhere. That is, it's continuous on R, negative infinity to infinity. Any rational function is continuous, all right? Remember what an irrational function is from college algebra, okay? If you need some work on that, let me know, okay? That is, it is continuous on its domain, right, okay? Wherever it's defined. So basically, with a rational function, that pretty much means if you don't have division by 0, okay, with a rational function, awesome, good, okay? Cool, so that gives me two places. Well, are there any others? Yeah, there are some others. The following types of functions are continuous at every number in their domains. I want to be very careful here. It's not everywhere, it's in their domains. So you really want to think to yourself, what's the domain of this function? Okay? Polynomials. We already said that. They're continuous everywhere. Rational functions, as long as we're not dividing by 0. Root functions. Root functions, no negatives in the roots. All right? We're doing real calculus, not complex calculus, which you can do, but we're not doing it. Trigonometric functions. All right? Some of them are defined everywhere. The domain is everywhere, like cosine and sine. Others have a domain like tangent or cotangent. They have some restrictions on their domains. Inverse trigonometric functions. Think about those ones, right? Okay. Inverse trig functions. They've got restrictions for those ones. They have generally restrictions on their ranges, okay, and not on their domains. Exponential functions. Same thing, right? Okay. Exponential functions frequently are continuous everywhere. Okay. Logarithmic functions. Well, that's one from your review, right? Remember that a log is not going to be defined at x less than 0. Okay, x less than or equal to 0, excuse me. So natural log of 0 does not exist. Anything negative is also not going to exist. All right? So just review the domain of these functions. All right? So now let's take a look at an example as to how we're going to use something like this. So let's look at this particular one, let's define the interval on which f of x equals the square root of x squared plus 1 over x minus 1 is continuous. All right? So if we remember this thing, let's imagine that f of x equals, and we're going to call it g of x over h of x. All right? It's basically a division. So if you remember, that's kind of like that division one that we had there. Okay? So g of x is a root function. Okay? And h of x is a polynomial. H of x is continuous everywhere. And then g of x, a little bit more complicated, right? G of x is defined for x squared plus 1 greater than or equal to 0. Okay, x squared plus 1 is greater than or equal to 0, right? So if I look at this, I now need to say, okay, well, what's the domain for g of x? Because if you remember, right, we'll go back up to our theorems. Okay, we go back up to our theorems. Our theorems say, well, any rational function is continuous wherever it is defined. That's great. Okay, and the following types of functions are continuous at every number in their domain. So we're going to have to actually define what their domain is, or what the domain here is. Okay. So we've got to think about what's the domain of the square root of x squared plus 1. Okay? The domain of x squared plus 1 is x squared plus 1 greater than or equal to 0. Okay? Well, since x is squared, and we are adding 1, okay, we are adding a positive number. X squared plus 1 is always positive. So, the domain of the square root of x squared plus 1 is equal to negative infinity to infinity. It's defined everywhere. Okay? We said h of x, our bottom function, okay, is also defined everywhere. Right? But remember, we'll go back up to this last little piece, we've got f over g. They're defined everywhere. Great. Continuous everywhere. Right? Except for the fact that g of a is going to equal somewhere. It's going to equal 0 somewhere. Right? So, our problem point is g of 1, because g of 1 does not exist. Okay, so g of 1 does not exist, so we've got a problem there. Well, that's okay, that's fine. It's defined everywhere else. We're just going to say that f of x is continuous on the intervals negative infinity to 1 and union 1 to infinity. Okay? So as long as we pull out, the 1 out of that function, right? Or as long as we pull out the 1 out of the domain, then what we get is something that's continuous everywhere except for at 1. Okay? So let's look at what exactly we did here. Okay? Because this is an explanation. It's a mathematical explanation. And continuity is going to be different because it does a lot of this kind of stuff. Okay? So I look here. I'm going to define the interval on which f of x equals the square root of x squared plus 1 over x minus 1 is continuous. Now, this is a rational, or this is a division of two functions. So I'm going to think about each one of the functions, the top and the bottom individually. G of x, that's a root function, okay, which I have in my previous theorem says that it's going to end up being defined or continuous everywhere on its domain. Well, its domain is going to be when x squared plus 1 is greater than or equal to 0, right? which just happens to be everywhere. So you got to test that. You got to see, okay, where is that actually going to give me greater than or equal to 0? On the bottom is a polynomial. It's defined everywhere. So since it's defined for all values of x, we're good there. But then we've got a third piece, and the third piece is this function as a whole, okay, is not going to be defined when x equals 1, because that makes the bottom 0. And since the bottom is 0, that says, okay, that's going to give us a discontinuity. So we put all three of those together. We bring them all together, and what we get there is when we put them all together, we just get that x equals 1 is the only place where we're going to have the discontinuity. Okay? So this function is going to be continuous everywhere except at x equals 1. And that kind of tells you how to think about or to imagine what it means to be continuous on an interval and how to prove that something's actually continuous on an interval. All right, so this concludes the lesson. We've looked at here continuity from a lot of different perspectives. So this is one of our longer mini lectures. We've looked at it from the perspective of what is the definition of continuity, and then how do we use that definition to prove that something's continuous. Then we talked a little bit more about that concept of continuity, the idea of no breaks in the function. Okay? No breaks in the function. Then we talked about the different kinds of discontinuities that we could have and how we can identify them visually and also what we call analytically. That is when we use the calculus. And then finally we talked about being continuous on an interval. Okay? So we started out with continuous at a point, right? And we finished with this continuous on an interval, right? Be careful when you're reading, okay, that you're looking at, are you being asked for continuous at a point? Or are you being asked for continuous at an interval? Okay? Because they're very different, right? They're very different and they're proven in different ways. And even though their concepts are actually pretty similar. All right, so this concludes the lesson.